So let's take a look at vectors. So this is our last lecture slideshow for Chapter 1. And Chapter 1 is just an introductory chapter, but let's look at some of the conventions that we use in physics. So first off, this is a vector, and it has both size and direction. Now this one happens to represent velocity. Down here, this vector is heading to the right, and this vector represents force. Now, the interesting thing about vectors, it's a term that's used and it encompasses many concepts that we look at in physics. Vectors is anything that has size and direction. So you'll be memorizing that. You'll need to memorize it, and there's many example of vectors, and you'll need to memorize those too because we use vector a lot of math on the vectors. Actually, not, I wouldn't say a lot of math, but you do quite a bit, and you need to know if something is a vector versus a scalar, and a scalar just has magnitude only. So, but we use vectors, and we use Pythagorean theorem and SOHCAHTOA on these vectors. So let's take a look at these. So displacement vector. So displacement vector starts at an initial position, ends at a final position. This is very specific, and a displacement vector compared to distance. This is distance. I'm a boat. Here I go. Oh, I've gone on this path. I keep going. Oh, isn't this nice? But boom. That's the distance traveled right there. Now, distance is a scalar. It has magnitude only, and that's significantly different than our displacement vector, where we say, listen, you started here, here's your initial position, and this is your final position. Notice along I'm traveling along, this is a displacement vector, and vectors are represented by arrows. So displacement vector arrow in this textbook, they use blue, whereas the slide before we saw velocity was green and force was red. So very specific definition for displacement as compared to distance. All right, so let's take a look here. Let's practice drawing some motion diagrams using vectors, displacement vectors. So in this case, for this slideshow, they're going to be using blue. So if you want to pause this and try it yourself, that'd be great. I'm going to go ahead and put it on the next slide here so you can see the solution. But basically, we have Alice sliding along smooth. All of a sudden, she hits a snowbank, and it brings her to a halt. So actually sounds a little fun. So here's Alice. So from here to here, that's our displacement vector, and a certain amount of an increment of time. Same thing here, here. So these first three displacement vector arrows are the same size. That means she's moving at a constant speed. All of a sudden she hits a snowbank, and we can tell that because equal increments of time, the displacement vectors get smaller and smaller. So she's covering less distance in the same increments of time. She's slowing down. So right here, displacement vector, we can add displacement vector. Sam starts here, heads east, and then he heads northeast here. So if I ask for a displacement vector, what is his net displacement? I have to start from the very beginning of the first vector and draw this vector arrow to the tip of the second, so the arrow of the second. So this is how we add displacement vectors. We call this the tip-to-tail method. Let's practice another one. So adding vectors, and this could be force, velocity, displacement. These are all vector quantities and with directions. So we can use these arrows. So if we want to add A and B, draw A, tip to tail. You put the tail of B on the tip of A, and then you start from the very tail of A. You draw a vector to the tip of B, and that is your A plus B, and that's also your net. In this case, since these are blue, it would be displacement, net displacement vector. Doesn't matter the order you add B or A, because vectors keep the same distance and orientation. So we could slide this around. We could do B plus A, and if you moved A over here, you'd still get the same net displacement vector, same direction, and it would be the same length, which would be magnitude for the vector. All right, so let's take a look at, practice this yourself. You can hit pause on this, and then I'll go to the next slide so you can see the solution. So Jenny runs 1 mile northeast and then 1 mile south. Graphically find her net displacement. So you're using the tip-to-tail method practice on this, and here it is. Solution. So The red vector represents Jenny's net displacement. And at any time during the slideshow, you are welcome to pause if you need to take a look at how the problem was done or the solution, or you can rewind and hear it again to see what was said about adding tip to tail and then drawing from the tail of the first to the tip of the second. Okay, so the interesting thing here, I like looking at displacement and velocity vectors, and the reason is when you have a displacement and velocity vectors stacked up like this, it's no surprise that the displacement and the velocity are in the same direction. You have to be moving in a direction to displace in that direction. So you could see here the displacement is getting greater over equal increments of time, and what that means is if you're covering more ground over equal increments of time, you are speeding up. So these velocity vectors are getting longer and longer. The car is speeding up. So let's take a look here at our SOHCAHTOA. So the nice thing using SOHCAHTOA and Pythagorean theorem, we're going to see a lot of right triangles. And with right triangles here, you've done right triangles before. This Pythagorean theorem, this is from way back when. This SOHCAHTOA, though, this trig function, this may be recent to you in your math class. The nice thing is if you only have two of these variables, that's all you need. Everything's three variables. So if you have two and you know how to use them, and you know how to use Pythagorean theorem, and you know how to use SOHCAHTOA, and your calculator is set in degrees, not radians, you can find out all sorts of things about a right triangle. Now, what's the big thing about a right triangle? The big thing about a right triangle is a lot of things we look at in physics, they end up being right triangles. So these tools are going to be very helpful for you. You know, physics is not a math class. It is, you need to understand what the physics concepts are before you can even apply the math. There's some math, but it is most certainly not a math class. So here's a first practice using Pythagorean theorem. I'll let you hit pause and check that out if you need to. That's just for your benefit, but most of you are really familiar with Pythagorean theorem. So let's move on. So if you have three legs of a triangle, the adjacent, opposite, and hypotenuse, what does this mean to us? What's the big deal? Everything is in reference to theta. And theta in the triangle, now we're not talking about the angle 90 degrees. We know where 90-degree angle is in a right triangle. We're talking about the other two angles in that. And we all know, it adds up to 180, which is terrific to know. Because if you know two of them, you can figure out the last one. But you usually don't need to go that far with something. It's not a triangles class here. But we are going to use this tool to figure out different things that are happening physically and different events. So that's what we call it a physics class. Different events are occurring physically, and we'll use this tool. Let's start using it. So anyways, we know that the longest leg is the hypotenuse. What about the other two legs? So let's see. Got to know where theta is. Now, if theta is given to you, then that's fine. Let's say theta's here on the left-hand side right there. So the opposite leg is here because it's opposite of theta. The adjacent leg is here because it's adjacent or next to theta. We already know this is hypotenuse. Kids never miss that. They know the longest leg is the hypotenuse. So now you've labeled your legs and you're ready to use the SOHCAHTOA because you know your parts of your right triangle. So this is an example of where theta is not given to you, and I just picked where I wanted to put it, upper right hand corner right here, and so that makes this the opposite leg and the adjacent leg. I had to put it myself, and many times you're going to have to put it in yourself too. So you just look at what you're given and then see where you can go. Alright, so here's an example, and given two legs of this right triangle, solve for theta. So you've been given 3 meters and 5 meters. So solve for theta. I gave you theta. So you were given theta. So here it is. And you look here, the 3 meters is opposite and the 5 meters is adjacent. So let's use the function that has the opposite and the adjacent. Isn't that a good idea? Yeah, let's do that. So we're going to use tangent of theta equals opposite over adjacent. This is the TOA of the SOHCAHTOA. So the TOA. So there's your TOA. That's where that came from. So for this move here, for theta, you're going to have to divide the other side by tangent. So here it is. So we have inverse tangent. And you can access that on your calculator. If you hit the shift key and the tan key, you'll see above it has a tangent with a -1 to the -1 power. So we call this our inverse tangent, and the opposite leg was 3 meters, adjacent's 5 meters, the meters cancel, and make sure your calculator's in degrees, not radians, and when you punch it in, boom, 31 degrees. So the answer for this one is 31 degrees. So you're going to try practice one here. Hit pause on your slideshow, and I will pop to the next screen so you can see the solution. And there it is, 37 degrees. So for this one, this is practice picking which function, so, ca, or the toa. So let's say you were given this leg down here, and you were given this leg over here, and you choose here. You choose to put theta in there. What function would you use? Well, if you have the opposite leg and the adjacent leg, you're choosing to use the tangent theta equals opposite over adjacent. How about if you're given the hypotenuse and then over here this leg, and then you chose to put theta in here. You're like, I'm going to put theta in right there because these two were given here. I'm putting theta in here. This makes this the opposite leg. This is the hypotenuse. You're going to use the so or the SOHCAHTOA because it has the opposite leg given and the hypotenuse given. So this is the function you would use. Last but not least, let's say you're given the hypotenuse and you're given this leg here. You chose to put theta here. You're like, okay, this is the adjacent leg. This is the hypotenuse. I'm using this one. Adjacent leg, hypotenuse. Oh, I'm using the ka of the SOHCAHTOA. So you'll end up using that, and that'll get you where you need to go. Last but not least, this is an example of a ball being thrown at 60-degree angle. It doesn't really say what the velocity is Jake launches this ball at, and we really, at this point, really don't care. But he launches the ball. What are the net velocity vectors? And this is what they look like. So this is a taking off, and you've seen a ball thrown through the air. Kind of seems like it slows a little bit at the top because it does, and then it heads back down and it speeds back up. So why might this be useful to us? This is why. So this is how we're going to be using right triangles. So in this example, Jake throws a ball at 60 degrees into the air, and Jim's on the other side. He's going to catch it. And look at this thing. Here are all the net displacement or velocity vectors. And the nice thing is if we've been given the angle, 60 degrees, which you were in the problem, I just made this up. I just said Jake launches this thing at 30 meters per second. This makes a right triangle, and there's horizontal and vertical velocity components, and we have to treat them separately, as you'll see in the next two chapters when we're dealing with acceleration. So this is how we're going to start using right triangles, and you're going to see pretty much right triangles for the rest of the year. It's a recurring theme. So, and that's the end of the slideshows for Chapter 1.